Bridging the divide between science and mysticism. Quantum entanglement. Bridging the divide between science and mysticism. The year 2022 marked a significant milestone in the annals of scientific achievement, as the Nobel Prize in Physics was awarded to three luminaries: Alain Aspect, John Clauser, and Anton Zeilinger. Their groundbreaking experiments with entangled particles have not only revolutionized our understanding of the quantum realm, but have also challenged the very fabric of reality, as perceived through classical physics. This accolade recognizes their collective efforts in providing compelling evidence against local realism, fundamentally altering our comprehension of the universe's underlying principles. The genesis of quantum entanglement. To appreciate the magnitude of Aspect, Clauser, and Zeilinger's contributions, it is essential to trace the origins of the concept of quantum entanglement. The phenomenon was first theorized in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen, in what is now famously known as the EPR paradox. Einstein, a staunch advocate of local realism, the belief that particles possess definite properties and are only influenced by their immediate surroundings, proposed a thought experiment that highlighted the peculiarities of quantum mechanics. The EPR paradox was intended to demonstrate that quantum mechanics, as it stood, was incomplete, suggesting the necessity for hidden variables that could account for the seemingly instantaneous connections between entangled particles. Bell's theorem, a turning point. The theoretical groundwork laid by Einstein and his colleagues remained largely unchallenged until 1964, when physicist John Bell introduced Bell's theorem. Bell sought to provide a way to empirically test the validity of local realism against the predictions of quantum mechanics. His theorem proposed inequalities, now known as Bell inequalities, that could be measured experimentally. According to Bell, if these inequalities were violated, it would provide evidence against local realism and in favor of quantum entanglement. Bell's theorem was revolutionary because it transformed a philosophical debate into an experimentally verifiable scientific inquiry. It set the stage for subsequent experiments that would either uphold or refute the principles of local realism. Pioneering experiments. Aspect, Clauser, and Zeilinger. The path from Bell's theoretical propositions to empirical validation was paved by the meticulous experiments conducted by Alain Aspect, John Clauser, and Anton Zeilinger. Each of these physicists made significant contributions that collectively solidified the case for quantum entanglement. John Clauser. In the early 1970s, John Clauser, along with Stuart Friedman, conducted the first experimental test of Bell's inequalities. Utilizing polarized photons, Clauser's experiments provided the first clear evidence that violated Bell's inequalities, thus challenging the notion of local realism. His work demonstrated that entangled particles could exhibit correlations that could not be explained by any local hidden variable theory, lending strong support to the predictions of quantum mechanics. Alain Aspect. Building upon Clauser's pioneering work, Alain Aspect embarked on a series of experiments in the early 1980s that refined the test of Bell's inequalities. Aspect's experiments addressed potential loopholes in previous tests, particularly the detection loophole and the locality loophole. By ensuring that the measurement settings were changed rapidly and ensuring that the measurements were space-like separated, Aspect's work provided even more robust evidence against local realism. His experiments conclusively demonstrated that entangled particles remained interconnected regardless of the distance separating them, thereby reinforcing the non-local nature of quantum mechanics. Anton Zeilinger. Anton Zeilinger extended the exploration of quantum entanglement beyond foundational tests of Bell's inequalities to practical applications. His work in quantum teleportation and quantum cryptography has been instrumental in demonstrating the potential of entangled particles for developing quantum technologies. Zeilinger's experiments have shown that entanglement can be harnessed for secure communication, paving the way for advancements in quantum computing and information processing. Quantum entanglement. Challenging local realism. At the heart of the Nobel-recognized work of Aspect, Clauser, and Zeilinger lies the challenge to local realism. Local realism is a classical notion that posits that particles have definite properties independent of observation, and that these properties are only influenced by their immediate environment. Quantum entanglement, however, defies this intuition by demonstrating that entangled particles remain interconnected regardless of the distance between them. This interconnection implies that the state of one particle instantaneously influences the state of the other, a phenomenon that seemingly violates the principle of locality, the idea that objects are only directly influenced by their immediate surroundings. The experiments conducted by these physicists showed that the correlations between entangled particles could not be explained by any theory that adhered to local realism. Instead, the results were consistent with the predictions of quantum mechanics, which allow for entangled particles to exhibit correlations that transcend classical constraints. This fundamental shift challenges our classical understanding of separability and independence, suggesting that the universe operates on principles that are profoundly different from our macroscopic experiences. Implications for quantum mechanics and quantum technologies. From a quantum physicist's perspective, the validation of quantum entanglement has far-reaching implications for both the theoretical framework of quantum mechanics and the practical development of quantum technologies. Advancements in quantum computing. Quantum entanglement is a cornerstone of quantum computing. The ability to entangle qubits, the quantum counterparts of classical bits, enables quantum computers to perform complex calculations at speeds unattainable by classical computers. Entangled qubits can exist in multiple states simultaneously, allowing quantum computers to process vast amounts of data in parallel. The work of Aspect, Clauser, and Zeilinger provides the empirical foundation necessary for scaling quantum computers, pushing the boundaries of computational capabilities. Secure communication. Quantum entanglement is also pivotal in the realm of secure communication. Quantum key distribution, QKD, leverages entangled particles to create encryption keys that are theoretically immune to eavesdropping. Any attempt to intercept the entangled particles would disrupt their quantum state, alerting the communicating parties to the presence of an intruder. This secure form of communication promises to revolutionize data security, safeguarding information in an increasingly digital and interconnected world. Enhanced measurement techniques. The principles of quantum entanglement have led to the development of advanced measurement techniques that surpass classical limits. Quantum metrology utilizes entangled particles to achieve higher precision in measurements, which has applications in fields ranging from gravitational wave detection to medical imaging. The enhanced sensitivity provided by entangled particles allows for more accurate and reliable data collection, driving progress in both scientific research and practical applications. Reinforcing the non-local nature of quantum mechanics. The experimental validation of quantum entanglement reinforces the non-local nature of quantum mechanics, challenging classical intuitions about the separability and independence of distant objects. This shift necessitates a re-examination of fundamental concepts in physics, prompting theorists to explore new frameworks that accommodate the non-local interactions observed in entangled systems. The ongoing dialogue between theory and experiment continues to refine our understanding of the quantum realm, pushing the boundaries of what is known and what remains to be discovered. The mystic's perspective. Quantum entanglement and ancient wisdom. While the scientific implications of quantum entanglement are profound, its resonance extends beyond the laboratory, bridging the gap between empirical science and ancient philosophical and spiritual concepts. From a mystic's viewpoint, the interconnectedness revealed by quantum entanglement aligns with age-old beliefs about the unity and interrelation of all things in the universe. Ancient philosophical concepts of unity. Many ancient philosophical traditions, such as those found in Eastern philosophies like Taoism and Buddhism, emphasize the interconnectedness and interdependence of all existence. The idea that particles can influence each other instantaneously across vast distances mirrors the mystical notion that the universe is a cohesive whole, where every part is intrinsically linked to every other. This convergence suggests that modern physics is uncovering truths that ancient wisdom has long intimated, albeit in metaphorical terms. The enigma of consciousness. The implications of quantum entanglement also extend to the nature of consciousness. Some mystical traditions propose that consciousness is a fundamental aspect of the universe, intricately connected to the fabric of reality. The indeterminate nature of quantum states, where particles do not possess definite properties until measured, parallels the idea that consciousness plays a role in shaping reality. This has led to intriguing dialogues between physicists and philosophers about the potential connections between quantum mechanics and the nature of consciousness. Holistic views of the universe. Quantum entanglement supports holistic views of the universe, where the boundaries between objects become blurred, and the focus shifts to the relationships and interactions that define existence. This holistic perspective is reminiscent of indigenous and shamanic traditions that view the cosmos as an interconnected web of life, where every action reverberates through the entire system. The scientific validation of such interconnectedness through quantum entanglement provides a tangible bridge between empirical evidence and holistic philosophies. Bridging science and philosophy. The work of Aspect, Clauser, and Zeilinger serves as a bridge between empirical science and philosophical inquiry, offering a more nuanced appreciation of the enigmatic and interconnected fabric of reality. This intersection invites a deeper contemplation of the nature of reality, consciousness, and the universe's underlying unity. Quantum mechanics and ontology. Ontology, the philosophical study of being and existence, finds a rich field of exploration in the context of quantum mechanics. The indeterminate nature of quantum states challenges classical notions of objective reality, prompting philosophers to reconsider concepts such as causality, determinism, and the nature of existence itself. The empirical findings of quantum entanglement provide concrete data that fuel these philosophical debates, leading to a more integrated understanding of reality. The role of observation. Quantum mechanics has long grappled with the role of observation in determining the state of a system. The fact that particles do not possess definite properties until measured raises profound questions about the nature of reality, independent of observation. This paradox has philosophical implications regarding the observer's role in shaping reality, leading to discussions about the interplay between consciousness and the physical world. Ethical and societal implications. The advancements in quantum technologies, spurred by the understanding of quantum entanglement, also carry ethical and societal implications. Quantum computing, while promising unprecedented computational power, raises concerns about privacy and security, particularly in the realm of cryptography. Quantum communication technologies offer enhanced security, but also present challenges in terms of accessibility and control. These considerations necessitate a dialogue between scientists, ethicists, policymakers, and the public to navigate the responsible development and deployment of quantum technology. The future of quantum entanglement research. The recognition of Aspect, Clauser, and Zeilinger with the Nobel Prize in Physics underscores the pivotal role of quantum entanglement in the future of scientific discovery and technological innovation. As research continues to unfold, several key areas are poised for significant advancements. Quantum networks and the Internet. The development of quantum networks, often referred to as the quantum internet, relies heavily on entangled particles to enable secure and instantaneous communication across vast distances. This emerging technology promises to revolutionize data transmission, offering unprecedented speeds and security measures that are impervious to conventional eavesdropping techniques. Quantum computing scalability. While quantum computers have demonstrated remarkable potential, scaling them to handle practical, large-scale computations remains a significant challenge. Ongoing research aims to develop more stable and scalable qubits, leveraging entanglement to enhance computational capacity and error correction mechanisms. Achieving scalable quantum computing will unlock new possibilities in fields such as drug discovery, materials science, and artificial intelligence. Fundamental physics and unification theories. Quantum entanglement continues to play a crucial role in the quest for unification theories that seek to reconcile quantum mechanics with general relativity. Understanding the interplay between entanglement and spacetime could provide insights into the nature of gravity, black holes, and the origins of the universe. This line of inquiry has the potential to bridge the gaps between different areas of physics, leading to a more comprehensive understanding of the cosmos. Interdisciplinary collaborations. The study of quantum entanglement fosters interdisciplinary collaborations that span physics, computer science, engineering, and even philosophy. These collaborations are essential for addressing the multifaceted challenges and opportunities presented by quantum technologies. By integrating diverse perspectives and expertise, the scientific community can accelerate the development and application of quantum innovations. The philosophical reverberations of quantum entanglement. Beyond its scientific and technological implications, quantum entanglement has profound philosophical reverberations that challenge our most fundamental assumptions about reality. Reconceiving reality. Quantum entanglement forces us to reconsider the nature of reality itself. The traditional view of a deterministic universe, where objects have definite properties and behaviors, is supplanted by a probabilistic framework where outcomes are inherently uncertain until measured. This reconception of reality aligns more closely with certain philosophical and spiritual traditions that emphasize the fluid and interconnected nature of existence. The illusion of separation. The entangled nature of particles dissolves the illusion of separation that is prevalent in classical physics. In the quantum realm, objects are not isolated entities, but are part of a larger, interconnected system. This dissolution of separateness echoes philosophical notions of unity and oneness, suggesting that the boundaries we perceive are perhaps more permeable and illusory than previously thought. The observer's role. The role of the observer in quantum mechanics has long been a subject of philosophical debate. The fact that observation collapses the wave function, determining the state of a particle, raises questions about the extent to which consciousness interacts with the physical world. This intersection between observer and observed challenges the dichotomy between mind and matter, inviting a more integrated view of consciousness and reality. Determinism versus indeterminism. Quantum entanglement epitomizes the shift from determinism to indeterminism in our understanding of the universe. While classical physics is grounded in predictable, deterministic laws, quantum mechanics embraces uncertainty and probabilistic outcomes. This shift has profound implications for free will, causality, and the nature of scientific laws, prompting a re-evaluation of how we conceptualize cause and effect in the universe. The symbiosis of science and mysticism. The recognition of quantum entanglement's dual resonance with both scientific inquiry and mystical philosophy highlights the symbiotic relationship between these seemingly disparate domains. Rather than being in conflict, science and mysticism can complement and enrich each other, providing a more holistic understanding of reality. Science illuminates mystical concepts. Scientific discoveries like quantum entanglement lend empirical weight to concepts that have been articulated in mystical and philosophical traditions for centuries. This illumination fosters a deeper appreciation of the interconnectedness and unity that these traditions have long espoused, bridging the gap between metaphorical wisdom and empirical evidence. Mysticism inspires scientific exploration. Conversely, mystical and philosophical perspectives can inspire new avenues of scientific exploration. The holistic and integrative views found in mystical traditions encourage scientists to think beyond reductionist paradigms, fostering creativity and innovation in theoretical and experimental approaches. A unified understanding of reality. The convergence of scientific and mystical insights through phenomena like quantum entanglement paves the way for a more unified understanding of reality. This integration acknowledges the complexity and multifaceted nature of the universe, embracing both the measurable and the ineffable aspects of existence. It encourages a worldview that honors both empirical rigor and the profound mysteries that continue to inspire human curiosity and wonder. Conclusion. A new paradigm of understanding. The Nobel Prize awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their work on quantum entanglement signifies more than just a scientific achievement. It heralds a new paradigm of understanding that transcends traditional boundaries. Their experiments have not only validated the counterintuitive predictions of quantum mechanics, but have also opened doors to technological innovations that promise to transform our world. Moreover, the implications of their work extend into the realms of philosophy and spirituality, offering a bridge between empirical science and ancient wisdom. Quantum entanglement challenges our classical notions of reality, separability, and determinism, inviting us to embrace a more nuanced and interconnected view of the universe. It underscores the intricate tapestry of existence, where every particle, every interaction, is woven into a cohesive whole. As we stand on the cusp of further advancements in quantum technologies and deepen our exploration of the quantum realm, the legacy of Aspect, Clauser, and Zeilinger will continue to inspire both scientific inquiry and philosophical contemplation. Their work exemplifies the profound synergy that arises when rigorous experimentation meets the timeless quest to understand the nature of reality, consciousness, and the universe's underlying unity. In essence, the Nobel-recognized work of Aspect, Clauser, and Zeilinger not only advances scientific understanding, but also bridges the gap between empirical science and philosophical inquiry. It offers a more nuanced appreciation of the enigmatic and interconnected fabric of reality, inviting us to ponder the mysteries that lie at the intersection of the observable and the unknown, the measurable and the mystical. The broader impact on education and public perception. The groundbreaking work of these physicists also has significant implications for education and public perception of science. Quantum mechanics, with its counterintuitive principles, often poses challenges in terms of accessibility and comprehension for the general public. However, the tangible demonstrations of entanglement and its applications can serve as powerful tools for science communication and education. Enhancing science education. Integrating the concepts of quantum entanglement into educational curricula can inspire a new generation of physicists and scientists. By highlighting the experimental breakthroughs and their implications, educators can foster a deeper interest and understanding of quantum mechanics. Practical demonstrations. such as quantum teleportation experiments, can make abstract concepts more tangible and engaging for students. Public engagement and appreciation. Public interest in quantum mechanics has surged in recent years, driven by popular media and the promise of quantum technologies. The Nobel Prize recognition amplifies this interest, providing a platform to educate the public about the significance of entanglement and its broader implications. Public lectures, documentaries, and interactive exhibits can demystify quantum mechanics, making it more accessible and appreciated by non-specialists. Promoting interdisciplinary learning. The intersection of quantum mechanics with philosophy and mysticism underscores the importance of interdisciplinary learning. Encouraging students and researchers to explore connections between science, philosophy, and the humanities can lead to more holistic and innovative approaches to understanding complex phenomena. This interdisciplinary focus fosters a more comprehensive educational experience, preparing individuals to navigate and contribute to a multifaceted world. Ethical considerations in quantum research. As with any powerful technology, the advancements in quantum mechanics and entanglement bring forth ethical considerations that must be addressed to ensure responsible development and deployment. Privacy and security. While quantum cryptography promises enhanced security, it also raises questions about privacy and the potential for misuse. Ensuring that quantum technologies are developed with robust ethical guidelines is essential to prevent unauthorized surveillance and protect individual privacy. Access and inequality. The high costs and technical expertise required for quantum technologies could exacerbate existing inequalities if access is limited to affluent regions or institutions. Efforts must be made to democratize access to quantum resources, ensuring that the benefits of these technologies are distributed equitably across society. Dual-use technologies. Quantum technologies have the potential for both beneficial and harmful applications. For instance, quantum computing could be used to solve complex problems in medicine and energy, but could also be harnessed for developing advanced weaponry. Establishing international agreements and ethical frameworks is crucial to mitigate the risks associated with dual-use technologies. Environmental impact. The development and deployment of quantum technologies, particularly quantum computers, require significant energy and resources. It is imperative to consider the environmental impact of these technologies and strive for sustainable practices in their production and operation. The philosophical quest for meaning. The intersection of quantum entanglement with philosophical and mystical concepts invites a deeper exploration of the quest for meaning that lies at the heart of human existence. The search for unity. The entangled nature of particles echoes the human desire for unity and interconnectedness. This pursuit transcends scientific inquiry, touching upon the fundamental human longing to understand our place in the cosmos and our relationship with the universe and each other. Consciousness and reality. The role of the observer in quantum mechanics sparks profound questions about the nature of consciousness and its relationship with reality. This inquiry delves into the philosophical realms of mind-body dualism, the nature of perception, and the essence of being, challenging us to reconcile our subjective experiences with objective realities. Existential reflections. The uncertainty and probabilistic nature of quantum mechanics resonate with existential themes of uncertainty, free will, and the search for purpose. Embracing the indeterminate aspects of reality can lead to a more flexible and resilient worldview, fostering a sense of wonder and openness to the mysteries that surround us. A harmonious future. Integrating science and philosophy. The Nobel Prize recognition of Aspect, Clauser, and Zeilinger signifies a harmonious future where science and philosophy coalesce to enrich our understanding of the universe. This integration holds the promise of a more comprehensive and meaningful exploration of reality, one that honors both the precision of empirical science and the depth of philosophical inquiry. Collaborative endeavors. Encouraging collaborations between scientists, philosophers, and spiritual leaders can lead to innovative approaches that bridge the gaps between different ways of knowing. These collaborative endeavors can foster a more inclusive and holistic understanding of complex phenomena, addressing questions that lie beyond the scope of any single discipline. Expanding the boundaries of knowledge. The interplay between quantum mechanics and philosophy expands the boundaries of knowledge, inviting us to explore the frontiers of what is known and venture into the realms of the unknown. This pursuit drives the advancement of both scientific and philosophical thought, propelling humanity towards ever greater heights of discovery and understanding. Cultivating a unified worldview. Integrating the insights from quantum entanglement into a unified worldview fosters a sense of interconnectedness and shared destiny. It encourages a global perspective that transcends individualistic and fragmented modes of thinking, promoting a more cohesive and compassionate approach to addressing the challenges and opportunities of the modern world. Final reflections. The awarding of the 2022 Nobel Prize in Physics to Alain Aspect, John Clauser, and Anton Zeilinger for their work on quantum entanglement is a testament to the profound impact of their research on both science and humanity. Their experiments have not only validated the existence of quantum entanglement, but have also ignited a dialogue that bridges the empirical and the philosophical, the scientific and the mystical. As we reflect on their achievements, we are reminded of the boundless curiosity and relentless pursuit of knowledge that drive human progress. The exploration of quantum entanglement exemplifies the synergy between theoretical insight and experimental rigor, revealing the intricate and interconnected nature of reality. In embracing the enigmatic beauty of quantum mechanics, we embark on a journey that transcends the confines of traditional disciplines, inviting us to ponder the deeper questions of existence, consciousness, and the universe's inherent unity. The legacy of Aspect, Clauser, and Zeilinger serves as an enduring inspiration, guiding us towards a future where science and philosophy coalesce to illuminate the mysteries of the cosmos and enrich our understanding of the profound interconnectedness that binds all things.